Hello, in this lecture we'll prove Stewart's theorem using two different methods. In a nutshell, Stewart's theorem yields a relation between the lengths of the sides in the triangle to the length of its CVN. In the drawing we have triangle ABC. We know that side AB of this triangle ABC, side AB equals to C units, side AC equals to B units, and side AC equals to A units in its length. In addition, we know that line segment AD equals to M units and line segment DC equals to N units. And the CVN in this triangle ABC, is line segment AD. The length of the CVN AD is equal to D units in its length. And I repeat again that Stewart's theorem yields a relation between the lengths of the sides in the triangle to the length of its CVN. And according to Stewart's theorem, b squared times m plus c squared times n equals to a, here we open brackets, inside the brackets we have d squared plus m times n. Okay? And we prove that this equation is true in two different methods. We start with the first method. In the first method, we'll do a construction from point A. We'll draw perpendicular on BC. So this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and BC is E. We define the length this line segment ED as X. We will define the length of line segment AE as H. What is the length of this line segment EC? From the drawing it is very easy to see that line segment EC equals to ED plus DC. So EC equals to ED, that is X, plus DC, that is N. So in conclusion, E equals to X plus N units in its length. And what is the length of this line segment BE? From the drawing it is very easy to see that BE equals to BD minus ED. Again, BD minus ED equals to BE. I write it down. BE equals to BD minus ED. So BE equals to BD. BD equals to M units in its length, so we substitute BD by M, and ED equals to X units in its length, so we substitute ED by M by X. Therefore, BE equals to M minus X units in its length. Yeah, this line segment BE equals to M minus X units in its length. In the next step, we will implement the Pythagoras theorem in the green right triangle AED. The green right triangle AED. According to the Pythagoras theorem, by PT is the version for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So, the hypotenuse in this right triangle AED is AD. Therefore, the square of the hypotenuse is AD squared. And it must be equal to the sum of the squares of the perpendiculars, that is to say, it must be equal to AE squared plus ED squared. I repeat again. According to the Pythagoras theorem, in the right triangle AD squared equals to AE squared plus AD squared. Okay. Here, AD equals to D units in its length, therefore AD squared is D squared, and it must be equal to the sum of the squares of the perpendiculars, that is to say, it must be equal to AE squared. AE is h, therefore AE squared is h squared plus ED squared. ED equals to x, therefore ED squared equals to x squared. In conclusion, we found out that according to the Pythagoras theorem, the right triangle AD, D squared equals to h squared plus x squared. Okay, in the next step, we focus on the right triangle AEC. On the right triangle AEC, by PT is evaluation from Pythagoras theorem. According to the Pythagoras theorem, on the right on the right triangle, it is partially green. Triangle AC, the square of the hypotenuse is AC square. The hypotenuse is AC, therefore the square of the hypotenuse is AC square. And it must be equal to the sum of the first of the perpendiculars. To say it must be equal to AE square plus EC square. I repeat again, according to the Pythagoras theorem, the right triangle AEC, AC square equals to AE square plus EC square. Again, AC square equals to AE square plus EC square. So, the hypotenuse AC equals to B, therefore the square of the hypotenuse is B square, and it must be equal to AE square. AE equals to H, therefore the square of AE square equals to H square plus EC square. EC equals to X%. Units in itself, therefore EC square equals to X% square. In conclusion, according to equation number 1, we found out that B square equals to H square plus X% square. We'll open the brackets on this side of this equation, equation number 1, and we get that according to equation number 1, B square equals to H square plus X% square equals to X square plus N square plus 2 times X times N. In this equation number 1, we have H square plus X square. We already found out that H square plus X square equals to D square. So we substitute H square plus X square in this equation number 1 by D square. So we do it now, we get that V square equals to H square plus X square is D square plus N square plus 2xn. According to equation number 1, B square equals to D square plus N square plus 2xn. In the next step, we focus on the right triangle, triangle AEB. Again, we focus on the right spin triangle, triangle AEB. The right spin triangle, triangle AEB by PT. The square of the hypotenuse equals to the sum of the sides of the perpendiculars. The hypotenuse is AB, therefore the square of the hypotenuse is AB square. and it must be equal to the sum of the source of the perpendiculars, that is to say it must be equal to AE square plus BE square. I repeat again. On the right pink triangle, triangle AB, according to the Pythagoras theorem, we get that AB square equals to AE square plus BE square. The hypotenuse AB in the right pink triangle, triangle AEB is C, therefore the square of the hypotenuse is C square, and it must be equal to AE square. AE is H, therefore AE square is H square, plus BE square. BE, side BE equals to x plus n, m minus x. Again, BE equals to m minus x units in its length. Therefore, BE square equals to m minus x square. In conclusion, we found out that in the right pink triangle, according to the Pythagoras theorem, C square equals to A square plus m minus x square. This is equation number 2. We'll open the brackets of this side of equation number 2, and we get that according to equation number 2, C square equals to H square plus m minus x square. M minus x square equals to, according to the algebraic identity, that a minus b square equals to a square plus b square minus 2 times ab, we get that m minus x square equals to m square plus x square minus 2 times m times x. So in this equation we have, equation number 2, we have h square plus x square, h square plus x square equals to d square here. According to this equation, we substitute h square plus x square in this equation, equation number 2 by d square, and we get that according to this equation, equation number 2, c square equals to h square plus x square is d square plus m square minus 2 times m times x. This is equation number 2. And we have already found out that according to equation number 1, b square equals to d square plus n square plus 2xn. So we have 2 equations here. In the next step, we create equation number 3 in the following way. We will multiply equation number 1 by n. Then we will multiply equation number 2 by n, and then we'll add the 2 equations with each other. This is equation number 3. Okay. So we do it in 2 steps. First of all, we'll do this operation in the left side of equation, in the right side of equation number 1 and equation number 2, and then we'll do the same operation on the left side of equation number 1 and equation number 2. So this is the right side of equation number 1, and we multiply it by m. So it is m times, here inside the brackets we have d square plus n square plus 2 times x times n. So we multiplied the right side of equation number 1 by m. In the next step we multiply the right side of equation number 2 by n. This is the right side of equation number 2, we multiply it by n. So it is n, inside the brackets we have d square plus m square minus 2 times m times x. And it must be equal to the multiplication of the left side of equation number 1 by m. In the left side of equation number 1 we have only b square, so it is mb square, plus the multiplication of the left side of equation number 2. This is the left side of equation number 2, we have only c square, we multiply it by n, so it is nc square. Okay. In the next step, we'll open the brackets on this side of equation number 3. And we'll get that according to equation number 3, we'll open the brackets of this expression. We have m times d square is md square, plus m times n square is mn square, plus m times 2xn is 2axmn, plus we'll open the brackets of this expression also. N times d square is nd square, plus n times m square is nm square, plus n times minus 2mx is minus 2xmn. And it must be equal to mb square plus nc square. Okay, this is equation number 3 after we open the brackets. So here we have plus 2xmn minus 2xmn is 0, so those two expressions will get cancelled. In the next step, we take out this square as a common factor from md square and also from nd square. So here we have d square was taken out as a common factor. What is left from md square after we took from it d square as a common factor? What is left is actually m plus nd square. What is left from nd square after we took from it d square as a common factor? What is left is actually m plus, in the next step we will take out mn as a common factor from this expression, n square, and from this expression nm square. So what is left from nm square after we took from it mn as a common factor? What is left is actually m plus mn square. What is left from mn square after we took from it mn as a common factor. What is left is actually n. And we have also here is equal to b square m plus c square n. In the next step, we take out m plus n as a common factor from those two expressions. So m plus n is taken out as a common factor. What is left from this square plus times m plus n after we took from it m plus n as a common factor? What is left is actually d square plus what is left from m plus n times mn after we took from it m plus n as a common factor. What is left is actually mn, and it is equal to b square m plus c square n. Actually, m plus n equals to a. It is very easy to see it from the drawing. Here we have in the original drawing side BC from one side equals to A, from the other side BC equals to BD plus BC. That is to say, BC equals to BD that is M plus BC that is N. So side BC in total equals to M plus N from one side, from the other side it is equal to A, therefore M plus N equals to A. Okay, M plus N equals to A. So we substitute m plus n in this equation number 3 by a, and we get that here m plus n equals to a. Inside the brackets we have d square plus mn, and it is equal to b square m plus c square n. And this is exactly the equation of Stewart's theorem. So we proved Stewart's theorem in the first method. In the next step I will present to you how to prove that Stewart's theorem is true in the second method. In the second method, we define this angle ADB as theta. Therefore, the adjacent angle ADC must be equal to 180 degrees minus theta. According to rule number 1, that the sum of the angles on one side of a straight line is equal to 180 degrees. BC is one side of triangle ABC, therefore it is absolutely a straight line. So if we focus on the upper side of the straight line BC, at point D, here the sum of the angles must be equal to 180 degrees according to rule number 1. Which angles we have at the upper side of BC at point D? We have here angle theta plus the missing angle. In total they must be equal to 180 degrees. According to rule number 1. Therefore, the missing angle must be equal to 180 degrees minus theta. Why? Because 180 degrees minus theta plus theta is 180 degrees, exactly according to rule number 1. In the next step, we will implement the law of cosines in the green triangle ABD, and also in the pink triangle ADC. I remind you What is the law of cosines? First of all, the law of cosines is true in any triangle. So this triangle ABC could be any triangle. The length of side AB is A units, side AC equals to B units in its length, and side BC equals to C units in its length. In addition, this angle BAC equals to theta. So, according to the law of cosines, this triangle ABC, C square equals to A square plus B square minus 2 times A times B times cosine theta. Okay. Here we'll add to this equation 2 times AB cosine theta, and we'll get the 2 times AB cosine theta plus C square equals to A square plus B square. In the next step, we'll subtract from this equation C square, and we'll get that 2 times AB cosine theta equals to A square plus B square minus C square. Then we'll divide this equation by 2 times AB, and finally we'll get that cosine theta equals to A square plus B square minus C square over 2 times A times B. So in this equation, in this triangle ABC, that could be any triangle, cosine theta equals to A square plus B square minus C square over 2 times A times B. So we implement the law of cosines. On the green triangle ABD. The green triangle ABD, according to the law of cosines, cosine theta equals to D square plus M square minus C square over 2 times D times M. Again, the green triangle AB, according to the law of cosines, cosine theta equals to D square plus M square minus C square over 2 times D times M. The next step, we implement the same law, the law of cosines, in the pink triangle ADC. According to the law of cosines, in the pink triangle ADC, cosine 180 degrees minus theta equals to D square plus N square minus B square over 2 times D times N. This equation number 2, is the implementation of the law of cosines in the pink triangle ADC. We have the trigonometric identity that cosine 180 degrees minus theta equals to minus cosine theta. So according to this trigonometric identity, cosine 180 degrees minus theta in this equation number 2, equals to minus cosine theta. is equal to d square plus n square minus b square over 2 times d times n. In the next step, we'll multiply this equation number 1, by minus 1. And we get that according to this equation number 1, cosine theta minus 1 is minus cosine theta, and it is equal to, we multiply also this side of the equation number 1 by minus 1, so it is minus, we'll open the brackets here, inside the brackets we'll have d square plus m square minus c square over 2 times d times m. So we have here two equations for the value of minus cosine theta. In the next step we'll create equation number 3 that states that minus cosine theta according to equation number 1 must be equal to minus cosine theta according to equation number 2. So minus cosine theta according to equation number 1 equals to minus d square plus m square minus c square over 2 times d times m, and it must be equal to minus cosine theta according to equation number 2. Minus cosine theta according to equation number 2 equals to d square plus n square minus b square over 2 times d times n. In the next step we will multiply this equation number 3 by 2d, and we get that according to equation number 3. So in this side of equation number 3 we have 2d over 2d is 1, so 2d will get cancelled, and in the denominator we left only with m, so we have m in the denominator. The denominator didn't change. It stays as minus d square plus m square minus c square, that is equal to, we multiply also this side of equation number 3 by 2d. 2d over 2d is 1, so in the denominator we left only with n, and the numerator didn't change. It remains d square plus n square minus b square. So in the next step we'll first multiply this equation number 3, and we get that according to equation number 3, here we have n or minus n. Inside the brackets we have d square plus m square minus c square equals to m times d square plus n square minus b square. So this is equation number 3 after we cross multiply it. In the next step we'll open the brackets on both sides of this equation number 3, and we get to the according to equation number 3. Here minus n times d square is minus nd square, minus m times m square is minus nm square, and finally minus n times minus c square is plus nc square. because minus times minus is plus. And is equal to, open the brackets also. On this side of equation number 3, we get that m times d squared is md squared, plus m times n squared is mn squared, plus m times minus b squared is minus mb squared. In the next step, we will add to this equation number 3, nd squared. So this is the equation number 3, we have nd squared minus nd squared is 0. We will add also to this equation number 3, nm squared. So in this side of equation number 3, we have nm squared minus nm squared is 0. And finally, we subtract from this equation number 3, nc squared. So nc squared minus nc squared is 0. So in total, this side of the equation, we left with 0 with nothing. And it is equal to md squared plus mn squared minus mb squared. And we have to add also to this side of equation number 3, nd squared. We also have to add to this side of equation number 3, nm squared. And finally, we have to subtract from this side of equation number 3, nc squared. Okay. In the next step, we take this square as a common factor from md squared and also from nd squared. So inside the brackets we have m plus n plus m, we take out mn as a common factor from mn squared and also from nm squared. So inside the brackets we have m plus n minus mb squared minus nc squared equals to 0. We add to this equation number 3, mb squared and also nc squared, and we get it according to this equation number 3, d squared m plus n plus mn m plus n equals to mb squared plus nc squared. The next step, we take out m plus n as a common factor from those two expressions. So m plus n is taken out as a common factor from those two expressions. So inside the brackets we left only with d squared plus mn, that is equal to mb squared plus nc squared. We already found out in the first method that m plus n equals to a. Therefore, we substitute m plus n in this equation number 3 by a, and we get that according to equation number 3, m plus n is a. Inside the brackets we have d squared plus mn, that is equal to b squared m plus c squared n. This is exactly the equation of Stewart's theorem. A d squared plus mn equals to b squared m plus c squared n. So we proved that Stewart's theorem is true according In the second method, in the next step, I'll summarize the lecture. We start with the first method. So, in this lecture, we proved Stewart's theorem in two different methods. In a nutshell, Stewart's theorem yields a relation between the lengths of the sides in a triangle to the length of its CVN. In this triangle ABC, the length of side AB is units, side AC equals to B units in its length, and side BC equals to A units in its length. Line segment BD equals to M units, line segment DC equals to N units, and AD, line segment AD is the CVN in this triangle ABC, and the length of the CVN AD is the units, and according to Stewart's theorem, in this triangle ABC, B squared times M plus C squared times N equals to A. We'll open brackets. Inside the brackets we have D squared plus M times N. We proved that this equation, Stewart's theorem, equation is true in two different methods. So, in the first method, from point A, we draw perpendicular on BC. This angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and BC as E. We define this line segment ED as X. We define the line segment AE as H. And here EC equals to X plus N. And BE equals to BD minus ED. BD is M, ED is X. Therefore, in total, BE equals to M minus X units. Line segment BE equals to M minus X units in its length. Then we implemented the Pythagoras theorem on the green triangle AED. According to the Pythagoras theorem, in the green triangle AED, AD square equals to AE square plus ED square. Again, AD square equals to AE square plus ED square. AD equals to D units in its length, AE equals to H units in its length, and ED equals to X units in its length. Therefore, we get that D square equals to H square plus X square. Then we focused on the right triangle AEC. In this right triangle, B square equals to AC square equals to AE square plus EC square. AC square equals to AE square plus EC square. AE equals to H, EC equals to X plus N, and AC equals to V. And therefore, we get here that B square equals to H square plus X plus N square. We open the brackets here, so B square equals to H square plus X plus N square equals to X square plus N square plus 2 times Xn. H square plus X square equals to D square according to this equation. So we substitute H square plus X square in this equation number 1 by D square, and we got that according to equation number 1, B square equals to D square plus N square plus 2 times Xn. Then we implemented the Pythagoras theorem on the right wing triangle AEB. According to the Pythagoras theorem, in the right wing triangle AEB, AB square equals to AE square plus BE square. B square equals to AE square plus BE square. Repeat again, the right wing triangle AB square equals to AE square plus EB square. The hypotenuse AB equals to 3 units, its length, A equals to h, and B equals to a minus x. Therefore, we get that according to Pythagoras theorem, c squared equals to a squared plus a minus x squared. We open the brackets here, and we got that c squared equals to a squared and a minus x squared equals to x squared, m squared plus x squared minus 2 times mx, according to the algebraic identity that a minus b squared equals to a squared plus b squared minus 2 times ab. We have here h squared plus x squared that is equal to d squared. So we substitute h squared plus x, h squared plus x squared equals to d squared. So we substitute h squared plus x squared in this equation number 2 by d squared. And we got that c squared equals to h squared plus x squared is d squared plus m squared minus 2mx. This is equation number 2, and according to equation number 1, we found out that b squared equals to d squared plus n squared plus 2 times xn. Then we created equation number 3 in the following way. We multiplied the equation number 1 by n. Then we multiplied the equation number 2 by n, and then we added the two equations together. This created equation number 3. Okay, so we did it in 2 steps. First of all, we multiplied the right side of equation number 1 by m and the right side of equation number 1 by n, and then multiplied the left side of equation number 1 by m and the left side of equation number 2 by n. And they must be equal to each other, of course. So here we multiplied the right side of equation number 1 by m. This is the right side of equation number 1, so it is m. Inside the brackets we have d squared plus n squared plus 2 times xn. Then we multiplied the right side of this equation number 1 by n. This is the right side of equation number 2. So it is n. Inside the brackets we have d squared plus m squared minus 2 times mx. And it must be equal to the multiplication of the left side of equation number 1 by m. Here we have on the left side b squared, so it is mb squared plus the multiplication of the left side of equation number 2 by n. In the left side of equation number 2 we have c squared, so it is nc squared. Okay. Then we open the brackets on this side of equation number 3 and found out that m times d squared is md squared, m times n squared is mn squared, n times 2xn is 2xmn. And we open the brackets here also, n times d squared is nd squared, plus n times m squared is nm squared, plus n times minus 2mx is minus 2xmn. And it must be equal to mb squared plus nc squared. This is equation number 3 after we open the brackets. So we have here plus 2xmn minus 2xmn is 0. So those two expressions will get cancelled. Then we took d squared as a common factor from md squared and nd squared. So inside the brackets we left only with m plus n. Then we took nm as a common factor from nm squared and from mn squared. So inside the brackets we left only with m plus n. And it is equal to b squared m plus c squared m. Then we took out m plus n as a common factor from those two expressions. So inside the brackets we left only with d squared plus mn, and it must be equal to b squared m plus c squared n. And m plus n equals to a. Here m plus n equals to a. From one side BC equals to m plus n. From the other side it is equal to a. Therefore m plus n equals to a. So substitute m plus n in this equation by a, and we got that m plus n is a. Inside the brackets we have d squared plus mn, and it is equal to b squared m plus c squared n, and this is exactly Stewart's theorem. Then we proved Stewart's theorem in a second method, In the second method, we defined this angle ADB as theta. Therefore, the missing angle must be equal to 180 degrees minus theta according to rule number 1, that the sum of the angles on one side of a straight line is equal to 180 degrees. Then we implemented the law of cosines on the green triangle and the pink triangle. According to the law of cosines, in any triangle, this triangle ABC could be any triangle. The law for side AB is A units, side AC equals to B units in length, and side BC equals to C units in length, angle BEC equals to theta. Then according to the law of cosines, C square equals to A square plus B square minus 2 times AB minus cosine theta. Okay, and from this equation we get that cosine theta equals to A square plus B square minus C square over 2 times AB. Okay, so in this equation cosine theta equals to A square plus B square minus C square over 2 times A times B. So we implemented the law of cosines on the pink triangle ABD. According to the law of cosines on the pink triangle ABD, cosine theta equals to M square plus D square minus C square over 2 times D times M. Okay, here cosine theta equals to D square plus M square minus C square over 2 times D times M. Then we implemented the law of cosines in the pink triangle ADC. According to the law of cosines in the pink triangle ADC, cosine 180 degrees minus theta equals to D square plus N square minus B square over 2 times D times N. Again, cosine theta equals to 180 degrees, cosine 180 degrees minus theta equals to D square plus N square minus B square over 2 times D times N. We have that trigonometric identity that cosine 180 degrees minus theta equals to minus cosine theta. Therefore, we substitute cosine 180 degrees minus theta in this equation number 2 by minus cosine theta. And according to equation number 2, minus cosine theta equals to D square plus N square minus B square over 2 times D times N. We multiply the equation number 1 by minus 1 and found out that according to equation number 1, minus cosine theta equals to D square plus M square minus C square over 2 times D times M. Then we have two different expressions for minus cosine theta. Then we created equation number 3 that states that minus cosine theta according to equation number 1 must be equal to minus cosine theta according to equation number 2. Minus cosine theta according to equation number 1 equals to minus D square plus M square minus C square over 2 times D times M, and it must be equal to minus cosine theta according to equation number 2. Minus cosine theta according to equation number 2 equals to D square plus N square minus B square over 2 times D times N. Then we multiplied this equation number 3 by 2D, and we got here 2D minus over 2D, 2D over 2D is 1, so in the denominator we left only with M. The numerator didn't change, it stays as minus D square plus M square minus C square, and it is equal to here 2D over 2D is 1, so in the denominator we left only with N. The numerator didn't change, it stays as D square plus N square minus B square. Then of course multiplied this equation number 3, and we found that according to equation number 3, minus N, D square plus M square minus C square equals to M. Inside the brackets we have D square plus N square minus B square. Then we open the brackets on both sides of this equation number 3, and we found out that minus N D square minus NM square minus N times minus C square is plus NC square equals to MD square plus MN square minus MB square. Then we added to this equation number 3 ND square, so here we have ND square minus ND square is 0. We added to this equation also MB square, so MB square, we have added NM square also, NM square minus NM square is 0. And finally, subtracted from this equation number 3, NC square. So NC square minus NC square is 0. So in this side of the equation we have 0. We did the sum operation on the left side, on the other side of course. So on the other side of equation number 3, we have already have the expression md square plus nm square plus mb square. So we have to add to this side of equation number 3 nd square, and also we have to add nm square, and we have to subtract nc square. Okay. Then we took this square as a common factor from md square and also from nd square, so inside the brackets we left only m plus n. Then we took nm as a common factor from nm square and from mn square, so inside the brackets we left only m plus n. Minus mb square minus nc square equals to 0. Then we added to this equation number 3, mb square plus nc square, and found out that this square m plus n plus nm plus nm m plus n equals to mb square plus nc square. Then we took out m plus n as a common factor from those two expressions, so inside the brackets we left with d square plus mn equals to mb square plus nc square. In the first method we already found out that m plus n equals to a, so we substitute m plus n here by a, in this equation by a, and found out that m plus n is a. Inside the brackets we have d square plus mn, and it is equal to b square m plus c square n. And this is exactly Stewart's equation. So we succeeded to prove that Stewart's theorem is true in two different methods. Okay, thank you very much.